All right, let's get started. So topic for today's lecture is network communities. So when you look at the structure of a network, you realize that there are parts of the network that looks, well, when you draw it, they look denser, right? Or more connected with the nodes, much more connected among themselves than with the rest of the network, right? So there are sort of groups of nodes, clusters, you can say communities. That's the way they usually called in social network analysis. So if I look at this picture, there is probably this group of nodes that are very tightly connected, right? There's a pretty high density. You can think about say of this group and that one, or maybe this whole thing. Then there is this group of nodes. You can think about this one as a community. This one is separate from everybody else, just floating in space, but it can also be thought of a community. Now, with the rest, well, it's not that clear, but you might also notice that there are probably some sort of higher connectivity patterns in here, in there. So these are all examples of communities, different communities, but in order to be able to detect them, and that's what we're going to be learning how to do today, we need to provide at least some sort of definition, right, that will allow us to search for the communities. So the definition is the following. So network communities are groups of vertices such that vertices inside the group connected with many more edges than between the groups, right? So the definition is a little bit vague, and allows for flexible interpretation, but there is a reason for that. In some way, it's the same as with when you work with data science or data mining, the definition of a cluster, what constitutes a good cluster. Now, in this sense, we can think about community detection as an assignment of vertices to communities, right? So on this picture, it's sort of again obvious, and it's very clear that we have three communities, right? This is probably following our definition. You can think about these three groups, but it's not always the case. Sometimes, as we will see on this slide, yes, sometimes you can actually see this very clear separation where you can literally, cut out some number of edges and get your communities. But then we might also encounter a situation like this, where we have a node that explicitly laying on the intersection of two groups, right? And so there is sort of this is a community and this is a community. And then node D is not exclusively belong to one community, but it actually can be assigned to two communities, right? And if I go back for a sec to the slide we started with, that's precisely the situation. Like there is this node which lays on the overlap of two communities. So then when we look at the definition, yes, community is assignment of vertices. Community detection is assignment of vertices to communities, but it's also possible to have an overlapping communities, and then a node can be assigned to two communities. All right. So looking for communities, we will distinguish the picture on the left, where the nodes will be exclusively assigned to one community, and picture on the right, where there is a possibility that the node is assigned to two communities. So picture on the left is called non-overlapping community. Picture on the right is overlapping community. Speaking of non-overlapping communities, you can clearly see, those of you who remember the previous lecture, that the problem of detecting these communities can be thought of as a problem of graph partitioning, because here we can actually cut, let me clear this first, we can actually cut out edges, and that will separate graph into the communities. On this side, yes, we can split yellow community from green, blue, but with this type of graph cut, we cannot split these communities. And so we're going to talk about two different types of algorithms, one for non-overlapping community detection, another one for overlapping community detection. All right. So what constitutes a community? What makes a community a community? And you know, this definition actually comes, or actually this explanation comes from the sort of the social network Bible of Wasserman and Faust, where community described as a cohesive subgroup. So there are, you know, mutuality of ties. So almost everyone in the group has ties to each other. Not necessarily everybody has ties to everybody, because if that's the case, then you get, you know, you get a clique, fully connected subgraph. I mean, it's still a community, but you don't get that very often, right? So we expect a lot of direct ties in between members of communities, but not necessarily all of them. And that's pretty much the same as the second point, that, you know, every node is almost reachable from each other node. There are, of course, higher frequency of ties within the group, and there is a separation, sort of low frequency of ties in between members of the group and the rest of the graph. If you think about social network, this is, you know, like any cult, right, or any tight group of friends. They are pretty much all of them know each other, and they have more connection internal than connections with sort of the rest of the graph, the rest of the society. So how can we quantify this notion of higher density of edges, right? More edges within the community than between? Well, you know, the sort of very straightforward definition can be actually just using graph density, right? The definition of a graph density. Now, we define the graph density in general in graphs as the ratio in between the number of edges that exist in the graph divided by the maximum possible number of edges, right? And if you have a complete graph, then the density is 1. If you have, you know, empty graph, density is 0. Everything is in between. So what you can think of is a definition of community internal density. So if you have, we have, you know, some graph, and we have some nodes and edges, and then let's say, I'll try to draw this briefly. Let's say, you know, there is this community, and then I'll put sort of some more pieces of graph, right? So what we can actually calculate is we can say, okay, look, if this is a community, for example, let's calculate number of edges that belongs to the community and divide it, knowing how many nodes belong to the community, because again, remember, partitioning our communities is determined by the node assignment. Then we just divide it by the total maximum number of edges that could be in that community, right? And that's going to be internal density. We can then also calculate external density, which is the edges that outside of the community. And then we can say, okay, look, let's compare those things, and we expect that internal density is greater than on average density in the graph, and external is less. So that's good, right? So if you determine the sort of, if we have this number of you know, if we know which nodes belong to the cluster, then we can actually calculate the density and try to compare it. Now, but that knowledge does not help us identify which nodes belong to the cluster. And if we, as we discussed it last time, you know, even splitting into two groups, it's going to be extremely difficult to go through all the possible combinations, factorial large number of combination, and leave alone, you know, splitting in multiple groups. So if we have groups, we can verify based on the density, but it's not easy density is not going to help us to determine those groups, to detect which nodes belongs to which group. At the same time, also, we have a challenge here that density is not sort of sensitive enough for us to identify precisely communities. So instead, people often use the notion of modularity. In fact, we already introduced once this metric when we talked about assortive distortive mixing. But the idea here is, again, we're going to compare the fraction of edges within the cluster, but now we're going to compare it not to sort of the density, not to the average density in the graph, but we're going to compare it to an expected fraction of edges if we had a random graph with a degree sequence the same as our graph. So it sort of tells us that if we have a random graph, it shouldn't have any communities, right? It's random, because random graph means every pair of nodes connected or not with some probability, right? And the probability is equal across the entire graph. And so you do not have sort of built-in notion of communities in there. So we expect the random graph not having any communities. But that gives you this sort of the level, the density you can compare against. And that's what Modularity Score does. It says, okay, let's take the actual number of the actual connectivity pattern between nodes and subtract the probability. This is the probability, the expected number of edges in between nodes of degrees ki and kj, and that's what it would be in a random graph, and add them up only for those nodes that belong to the same community. Delta ci cj, this is a Kronecker delta symbol, which is equal to 1 when ci is equal to cj, and then it's just normalization. Now, you can actually rewrite this formula in the following way. This is a ratio of number of internal edges to the total number of edges in the graph. So that reminds you about density, but then it is also sort of normalized, or you subtract, you contrast it against what you would have there if the graph was random. And that's computed the sum of node degrees within the community divided again by twice the number of edges. Now, this might look like a strange metric, and especially when you realize that this modularity score kind of goes from -1/2 to 1. And when you have a single community like graph as a whole, the modularity score is 0. That's the way this thing is set up. But it actually works surprisingly well. And it's used a lot for community detection. And here are the examples. Now, if we calculate, use that formula, and say the entire graph belongs to one community, here it's a green community, the modularity score is 0. Now, if we, for example, randomly assign here like every node to its own community, then you even get this modularity score is negative. We can think about, we can choose to have this partition, which is obviously not the best one, right? But let's go and calculate this modularity score for this partition, and it gets 0 to 2. And then this is sort of, we understand that this is probably the best partitioning, right? This is the best cluster, so you can the best communities, and this gives you the highest modularity score, right? So in this sense, the higher the modularity score, the better are the communities that we have. And again, this metric is very popular. It is not perfect, and sometimes it becomes sort of insensitive to small communities. When you have very small groups of nodes, this metric does not work too well. But other than that, it's quite it's quite robust. And we could use this in two ways. We could either try to take this metric and directly optimize it by trying different partitioning, just trying to maximize this metric. Or we can use some other approach, some sort of heuristics, but we can monitor the quality of the clusters by this metric. We can also check quality of the clusters by density, but again, this is used more often than just pure density. Any questions so far? Okay. So, as I mentioned before, we can actually think of community detection or formulate community detection through recursive graph partitioning. We learned last time that there are ways, for example, spectral algorithm to split the graph into pieces, and then we can actually continue cutting it until we get smaller pieces of the graph, and we can stop cutting, for example, when either modularity or density of those pieces becomes pretty high. And then as a result, you actually get the split of the graph into communities, right? So graph partitioning, recursive graph partitioning is the way to do community detection, right? In general, graph partitioning splits the graph into two pieces. That's not necessarily communities. But if you do it recursively, eventually you can end up splitting the graph into the communities. By doing this, again, you will assign all the nodes to different communities. And last time we talked about metrics that allows us to do it. And if you remember, we talked about the graph cut, which is just the number of edges that you need to cut. We talked about ratio cut, we talked about normalized cut, we talked about conductance, and the algorithms that we discussed in depth, sort of Laplacian, normalized Laplacian. We optimize this normalized cut by finding optimal partitioning. And that allowed us to find clusters. That's sort of one way you can do it. Today, we're going to talk about several other methods. And as I mentioned before, the graph partitioning or, community detection, cluster detection, this is an NP-hard problem. And so there is no, precise solution. So the Laplacian method, the one we discussed before, that was an approximation to the solution, right? We kind of formulated this as a integer programming, integer optimization problem, but we solved it eventually with relaxation method, which is an approximation. Today we're going to talk about very different approaches. We're going to talk about this heuristic approaches, where you think of some of sort of ideas, then try it, and if it works, great. It's usually greedy methods, which means they're not guaranteed to find you absolutely optimal partition, but in practice they're finding pretty good partitioning, and we can monitor through modularity the quality of the partition. So one of the method is called edge betweenness. And this method is similar to the method, graph cuts, because we're going to be cutting the edges, but it differs in the way we select the edges. If you remember, again, in the previous lectures, when we talked about the cut, we either just selected the partition, selected those edges that when you split the graph, you remove the smallest number of edges, or it was normalized, right? Normalized by the number of nodes in each partition. Now, edge betweenness actually based on a similar idea, but sort of slightly from a different angle. Now, we actually talked several lectures ago about the metric which is called node centrality, right? It was betweenness centrality. Now, can somebody remind me what betweenness centrality is? Remember, guys, we had degrees centrality.
How much we search in how much shortest paths it is.
Right. So betweenness centrality tells us of how many shortest path goes through a particular node. So Mark Newman introduced came up with a similar metric, but with respect to edges. He called it edge betweenness. And the idea is, Well, we can actually calculate for every edge, we can calculate how many shortest paths go through it. And if you think about, I don't know, St. Petersburg for a second, and the bridges over the Neva River, you realize that, yes, if you want to get from one part of the city to another, you will most likely have to go across the bridge, right? And so the bridge will lay on the lots and lots of shortest paths that takes you from one point in the city to another. And so that means that if you think again about that St. Petersburg, you will think about, okay, wait, but this is a partitioning into the clusters, right? Because every part of the city can be thought as a cluster in a sense. And so what we try to do is we want to find those bridges that have most shortest path going through them, right? And so the way to do it is really, through the definition of the edge betweenness. So we define edge betweenness as a number of shortest paths that goes through an edge. So we look at every edge, and then we go through all possible pairs of nodes and calculate how many shortest paths go through this edge, and normalize it by the total number of shortest paths from node S to node T. So we pick up one node here, this is S, this is T, calculate how many shortest paths goes from this guy to this guy and how many of them goes through each of those edges. In this case, none of them, but if I take this node and this node, there will be shortest paths here. If I take this node and this node, again, the shortest paths will go through here or maybe through here, maybe through both of them. And that's how you count the shortest path, that number that go through each edge. You define this edge betweenness, and then you start iteratively removing those edges that have the most number of shortest path going through them, because they are bridges. And so the idea, if you remove them, that would be the best way to split the graph into pieces. Does make sense? All right, so we calculate edge betweenness for each edge. We pick up the one that has the largest one and we remove it. Then we compute edge betweenness because shortest path would change, and again remove it, and so on and so on and so on. And that's the algorithm, right? So compute edge betweenness, remove edge with largest betweenness, and just keep doing it until the graph splits into two components. When that happens, you have two components. It's bipartite sort of graph partitioning. And then if you want, you can continue recursively for each of the partition, keep doing the same procedure. Now, we're not explicitly optimizing anything here. That's why it's heuristic, but the process leads to nice graph partitioning. So if you run this algorithm here, this is the partitioning we get, and that's sort of the dendrogram, the tree. The way to read it is exactly the same as you do for any clustering algorithm, right? This is sort of the first level split. So that's sort of how it goes. The first cut here is cutting this, and then you go deeper. It splits blue and green purple. So the next cut is here, etc., etc., etc. So that's edge betweenness algorithm. Now, interestingly, to see how it actually works, this is same graph. Zachary Karadik lab. If we do edge betweenness, this is the result. This is option partition. That's the partition that edge betweenness, the split, will do. Now we can actually keep splitting further and further, and that's what's going to be happening, right? If we run it again, that it will split those four nodes. And what I can do is we can actually measure the modularity score, as a function of number of clusters. So remember, when we have one cluster, so we sort of one community, when the graph is not split into pieces, modularity score is 0, right? And then, we split it into 2, 3, etc., 10 communities, 20 communities. And we monitor modularity score. And notice that in this case, modularity score is the largest when we have approximately, so it's 5, when we have 6 communities. Now, this is somewhat strange result here because I'm gonna show you on the next slide this split. So that's according to modularity score. This is the best possible split. Maybe, though, maybe this is not bad either. But when the graph is small, those metrics are probably not extremely sensitive, but this gives you an idea that modularity score, when you start definitely splitting it into many more pieces, which is obviously not right for such a small graph, modularity score keeps dropping and getting smaller and smaller and smaller and smaller. So, if not sort of 6, though, again, according to this idea that modularity score increases for optimal partitioning, then at least it's clear that, that's probably where your optimal number of clusters or optimal number of communities in this graph. Again, this is very similar to clustering problem where you don't really know how many clusters are optimal in the data. And this is a split, based on this edge betweenness of the graph for a dendrogram. Now, the problem with this method, though it actually works pretty well, it's robust, but the problem with it is that, every time you need to calculate the split, you need to go through, computing lots and lots of pairs to calculate betweenness, right? Because for each betweenness centrality, for each edge betweenness, you need to go through all possible pairs, right? Which is, order of n squared, and then you need to go through all the edges, which is m times n squared. So it's quite computationally intensive. Now, there are ways to approximate the number, the edge betweenness by sort of randomly sampling nodes, but still it becomes quite computationally intensive. And that a problem for a large graph, right? And typically, you don't want to do graph partitioning on the graph like we see it for 32 nodes. Nobody cares about it. But when you have several thousand nodes, that already becomes quite computationally expensive. But it's a good sort of algorithm to check on the smaller data, and it's pretty robust and it's sort of obvious, right? But at the same time, again, this is heuristic, so there is no sort of strict proof why it works and prove that it will work always. Now, here I want to talk about the method that is probably one of the sort of workhorses of today's graph or of today's community detection. It's called fast community unfolding. It's also called it's multi-resolution scalable methods. It's called also Lewin methods. And here is a demonstration of this method working on a pretty large 2 million people mobile phone network, 2 million nodes. So it's actually quite large. So this method is also a heuristic, right? There is no sort of global function that we optimize here, but on every step we do something smart, and on every step we sort of monitor modularity, and we just try in a greedy fashion to make only those steps in these algorithms that increases modularity, right? Because we know that optimal partition has the highest modularity score, so let's try to do steps that will increase it, and then it's a greedy algorithm, right? We'll not always succeed with it, or will not always get the best partition. But let's say if we repeat it multiple times or do something else smart, we might actually get pretty good solution. So how does it work? What does it do? So modularity is here, right? And it's going to be recomputed every time on every step of this algorithm. So the idea is the following. We start with every node being assigned to its own community. In this sense, it reminds you of this agglomerated clustering. Remember, sorry guys. Remember we talked about the graph partitioning, where we go top down, right? We go from we take the graph and we split it into pieces. Well, here it's sort of reverse process. We assign every node to its own community, to its own cluster, and then assemble them and grow those clusters by assembling those nodes. Okay, so we start with every node belonging to its own cluster, and then we will be checking if we take this node and its neighbor and put them in one cluster, if it's going to increase modularity or not. And we check it against all the neighbors of this node and pick up the one that gives us the highest increase in the modularity and merge them into one cluster. Then we go for the next, for the neighbor, and do it the same, and then for another neighbor, etc., 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 etc. So if we look at the picture, this is what it looks like. We start with every node belonging to its own cluster, and then we say, okay, let's look at the node, for example, 14 and its neighbor 8. If we merge them into one cluster, if it's going to increase modularity or not. Or if we merge sort of node 14 and 10 in one cluster. So to reassign them. And we go through all the nodes that are connected, right? So it's not all the past possible pairs of nodes. This is, you just follow the edges and see if it increases modularity. And if it does, you select the one that increases it the largest way, the assignment. And that, if you run it that way, for example, what we're going to see on this first iteration, we're going to see that, okay, there are sort of groups of nodes that become assigned to the clusters, right? So it used to be 1, 2, 3, 4, 5 different clusters when it started. But by doing this process, by following the edges and reassigning, it happens that the highest modularity will be achieved when this 5 belongs to one group, right? And then these guys will belong to another group, right? That forms the third group, that forms the last group. And then on the next step, what we're going to do is we're going to actually take those nodes and form a super node by literally collapsing them and putting a weight that corresponds to the number of edges that's being collapsed. And then we repeat this process, and then we repeat it again, again, and again, and again, until we pretty much end up with a sort of single cluster for the entire graph. So again, in the case of graph partitioning, we started with a graph, and then we keep splitting it until we get small clusters. Here we started with single nodes and merging them until we get big single cluster.
Like MST?
Going back, yes. Say it again.
It's very same for MST algorithm finding, as I know.
Minimal spanning tree, yeah, it's
Same idea.
It is, yeah, it's the same idea. It's the same idea. So again, there is a sort of two phases. On phase 1, we evaluate the modularity gain for merging, for sort of putting nodes in the same community, and select the node with which you get a better score, right? Then we place it there. We do it until there is no improvement, and then we merge nodes into the super nodes, and then again repeat it on this coarser graph, right? So it is sort of this, again, hierarchical approach. Now, you realize, if you think about this, that you realize that in this algorithm, it really depends on how you start it, right? It might give you different results, because if you started with node 2, it might say, okay, look, we look node 2, 1, and 4, and it might say, okay, node 2 is best, to have one node with node 1, and then we compare it, let's say, with other nodes, and we get certain clustering, right? But if I start, instead of starting with node 2, I start with node 5, it could be that node 5 looks and says, look, hey, what, we're better with some other node, and then let's say it might happen that this node will form a cluster. And so eventually, sorry guys, eventually you're going to get some sort of clustering, and that clustering will have a score that corresponds to it, and you run multiple scenarios, and you'll select the one that gives you the highest modularity. Sorry. Okay. So here is an example of this algorithm running on a quite complex graph. Yes.
In previous slide, could you please? Why blue node 4? It should be 3. Blue node.
Excuse me, which one? Which one?
In the right. Yes, blue node. Yes, 4.
4. Oh,
it should be 3. Or I.
Give me 1 second. So the idea is that when we merge things together, yeah, I think this is. Yeah, actually, I don't know. I'm surprised why the weight is that way. Good question. I don't know. I mean, what's important here is that the weight, the weights that are important for computing, that are very important, are the weights on edges.
The number of edge between blue and.
Yeah, I think so. I think so too, but I don't understand why it's 4 though.
Yes,
because it's not 4.
Yes, 3. The red is correct and the green correct, but blue 4. So I don't know.
Yeah, I don't know. We need to look it up, guys. I actually don't remember.
But it number. Yes, but sorry, it is number of edges. Yes.
I think. I mean, it would make sense. It's it should be either number of edges or number of nodes and edges, or one of those things. Please check and write email to the class with a correct answer. I actually do not remember from the top of my head, but let's see here. It's not. See what it says. Nodes merged into supernodes and weights on the links added up, right? And so we add up weights on the links. Initially, all weights were 1s, right? And when we had this, for example, in between dark blue and light blue, it's a weight 1. In between, red and blue, there are 3 edges, and it's a weight 3 here. So these numbers are very clear where they're coming from, right? So this is, this and this, and there is 1 edge. So that's where this 1. In between red and in between blue, there are 1, 2, 3 edges, and that's where this 3 comes from. And in between green and blue, there are 4 edges, and that's where this 4 comes from. Okay, so that's clear. Now, these numbers, that's what I am not quite sure about. I somehow thought, honestly, that would...
Maybe it's doubled internal?
Not really, because notice there are 3 of those blue nodes here,
Maybe
right?
it's
And
some
there's
No,
this
place
number.
within the-
internal, like in a modularity score calculating, like we have 2 edges in blue, so it's
Oh, well, I see what you're saying. Yeah, it could be. It looks like it because there is 1 edge here, and now it's 2. They're all even. Here is 14, and that's green. So 1, 2, 3, 4, 5, 6, 7. It could be, but guys, let's check. Let's check. I'm surprised that
It
they
is some
just,
degrees within the community, I think.
or it's number of degrees. Yes, that's also
so just
possible.
degrees, and my version is the same.
Because you remember that number of no, because it's what is it, 1, 2, 1, 2, 3, 4. No, there's more.
No, within the community, degrees
Within the
within the
community.
community. Yeah.
That is possible. That is also totally possible, right? Because this is going to be 1, 2, 3, 4, and the version is the same because remember that the sum of all degrees is equal to twice the number of edges because within the community, because because every 2 degrees give you an edge, right? But this one, if that's the case, then it is not only internal degrees, right? Because there's one. No, this is internal degrees. Then it's going to be internal degrees to community. Could be, guys. Okay, please check and write to everybody, right? I'm sure it's within the paper. It's actually specified precisely. Okay. All right. Let's move on. And so here is here is an example of this sort of this algorithm run on a pretty big graph with this hierarchical structure, and it still works pretty well, right? And so in fact, this is again this algorithm that literally everybody uses in large graphs these days. Okay, so that was this Blondel algorithm. There is another algorithm which is actually there are many more algorithms, but I want to point out some other algorithm which is also quite popular. It's agglomerative hierarchical clustering. Again, it's the notion of, okay, let's just try to agglomerate clusters. The idea here is slightly different. We for every pair of nodes, we build a similarity matrix that measures similarity between those nodes. And the similarity, in this case, and this is what the authors of algorithm wanted to use, and somehow it worked pretty well for them, is a number of common edges, minimum number of node degrees, plus 1 minus this what's called Heaviside step function, 0 for if x is negative and 1 for positive, so 1 for when there is an edge in between nodes. And then here's a graph. This is what the similarity metrics look like. Remember, we actually talked about node similarity. We had a lecture about node similarity. We used slightly different metric. We used Jacquard similarity. Well, here they introduced their own version of similarity that by some reason works well for the clustering. Again, guys, this is a heuristic method, heuristica, which means they don't have a very particular function. They're precisely optimizing compared to, say, that Laplacian, the graph Laplacian we did last time. They're just doing some sort of local procedures that they believe make some sense, right? And so the process here is you take, you take this matrix, you assign each node to a community on its own again, right? And you evaluate that similarity matrix, find the node pair with the highest similarity, right? So it's agglomerative clustering, merge them into a single community. Then you calculate the similarity between this community and the rest of the communities, and then just keep doing and doing and doing and doing. And you'll get again a tree, a dendrogram, and then you cut it on a certain level to get your partitioning. Now, again, this algorithm will work well for smaller graphs. It's not going to work too well for large graphs because the computational complexity of finding the node pair with comparing all the similarities with all other nodes, that's what will take lots and lots of time and computational effort. But here is an example of how it works on a smaller graph. On the smaller graph, it actually works pretty well. On a smaller graph, it should work pretty well. Notice, it's nice and clean, picture. All right. Okay. Sorry, guys, give me 1 second, and then we'll continue. All right, moving on. Now, here is a very, very different idea, but it's actually kind of pretty idea, right? Beautiful idea. So think again about, say St. Petersburg and the bridges, and think about this, you're walking in the city and you just do like random walk on the city, right? You kind of randomly walking the streets. Now, it's actually not a high chance that you will take the street that will end up with a bridge and you'll be able to cross it on the other side. And this corresponds to this notion then when you have a graph and you have a random walk tends to get trapped in the part of the graph with the higher densities. So, imagine that you start here, you randomly select where you go to. Well, there is 1/3 chance that you walk here. Then let's say you randomly select, there is 1/3 chance that you get here. Then, you get here, then you get here, then maybe you get here. But when you get here, there's only 25% chance that we will actually be able to leave this community, right? 25% because 1, 2, 3, actually 20%. There are 5 ways out, right? So it's only 1/5, 20% chance that you will leave the community even if you get to this node. All right. Okay. So if that happens, so that's the idea. The idea is to actually do random walks and see where those random walks kind of spend most of the time. And then communities will be those groups of nodes where your random walk spends most of the time. Now, it might sound sort of strange to run like random walks across the graph, but this algorithm can actually can work pretty well and be a very good algorithm if you have a very large graph and you don't want to detect all the communities, but you know a piece of the graph where you want to detect the community. And that's, you can like initiate random walk, see where a random walk spends most of the time, and that's going to be your community, right? So that's the idea here, the conceptual idea. Now, in practice, well, there are some algorithms, there are actually a bunch of algorithms that are based off this idea. One of them is called walk-trapped community detection. Again, the idea is that on every step, you actually make this random move and you get from one node to another node. Pij is going to be matrix, the probability to get from that node to another, from node I to node j. If they're adjacent, you normalize it by the node degree. And so that's sort of the same thing as what we did with the page rank, right? Because that was the random walk. And if you do t steps, that this can be described as this matrix to the power t, all right? And so the assumption of this algorithm, the theoretical assumption for this algorithm is that, if 2 nodes belong to the same community, if the probability to get from node I to node j in some number of steps is high, right? And then it's also, remember that there's this mutuality. So if you can get from one node to another, you can, of course, sort of get back. And so you can define you can define distance between nodes through these probabilities. Now, again, you could you could use this idea even without this mathematics by just literally randomly simulating random walk, but this math gives you sort of proofs that this process converges, right? And so you can define the distance between nodes. You can define the distance between nodes through this metric, right? And then you can actually use it to do some computations. Let's see how it works. So we compute the distance, and we can actually do this. We can do this by literally simulating, right? By simulating, or by actually sort of computations, right? So if we simulating, then we just literally run the random walk, calculate how many times it starts from node I, ended up at node K, and then we in T steps, and then approximate this probability as a ratio, this NIK over K over the number of random walks, and then we define distance between nodes, and then for communities we define distance between communities, and then we can measure that distance, right? And so whenever we have that distance, then we can after that, we can actually do again this agglomerative clustering approach, but now based on the distances that are defined through random walk, okay? And then, we start with single nodes assigning to its own community. Then we compute distance between adjacent community. Then we choose the closest community in terms of that random walk distance, merge them, and just keep going. Again, the beauty of this thing is that you can sort of center random walk in the part of the graph where you're interested in. And that's the result. Again, you're going to see the tree, right? The dendrogram that formed by this merging nodes based on this walking patterns. Okay, does make sense? All right. By the way, on one hand, we can actually just do exact simulation. On the other hand, if you don't care, if your graph is not very large, you can in fact do this on a sort of through matrix multiplication, and then if you do it through the matrix multiplication, it can be a large matrix, right? So again, it can be a simulation, and then you can just focus it on the part of the graph, or you can do those computations, those probabilities through matrix multiplication explicitly, but then you sort of deal with the entire graph if you do that. All right, so we talked about the algorithm that allows us to detect communities when you have a non-overlapping community, where you put every node to a single community. Now, if the situation is such that we have an overlapping communities, so we have a node that sits on the intersection of two communities, those methods where we look for edges, they're not going to work anymore, right? We cannot do the sort of graph partitioning, cutting edges out, simply because we have some nodes that are overlapping, right? That can be assigned to both communities. And here on this picture, for example, there is this node that belongs to two communities. If you look at this, communities based on their definition, or we can have even several nodes and even edge that can be an intersection, right? So there are different methods to do this. Now, this algorithm that we're going to discuss is quite interesting. It actually works well again on small graphs. This algorithm usually used for bioinformatics. not for social network analysis. So, but the idea for overlapping communities, yes, if you think about social networks for a second, yeah, you can have your friends community, your family community, your scientific community, and then you belong to all of them. So you just cannot cut out, any of the edges to split into the communities. So the idea here is called, the algorithm is called K-clique community detection. And the idea is to try to, use cliques or complete subgraphs. A K-clique is a complete subgraph with K nodes. Just to remind you, one node is a complete subgraph. This is a complete subgraph from 2 nodes. This is a complete subgraph with 3 nodes. This is a complete subgraph clique of 4 nodes, etc., right? So this method actually works, well for denser graphs, but that's where you most likely have this situation where you have overlapping communities. So the idea is that you try to detect those cliques and then look at their overlap. So here, for example, if I take a clique with 4 nodes, then A, B, C, D is a clique, and B, C, F, D are 2 cliques, right? And they overlap by those 3 nodes, right? And so here's the definition. 2 K cliques are said to be adjacent if they share K minus 1 nodes. So these are 4 cliques that we looked at. 4 cliques means they have 4 nodes, and they share 3 K minus 1, so 4 minus 1, 3 nodes. So these cliques, this one and this one are adjacent according to this definition. And on the picture on the right, they show various 4 cliques that are adjacent. Now, again, to have those 4 cliques, the graph should be pretty dense. Why do we do 4 cliques? Well, again, because that's sort of the way algorithm designed. But you can start with 3 clique, right? For example, there is this 3 clique, and here is another 3 clique, and they're adjacent with 2 nodes A and D, being adjacent here, right? They share those 2 nodes. So how does this algorithm work? Well, the idea is the following. Again, look at this picture. So we start with a clique, and again here I show you 3 clique, right? Over there it was 4 clique. This is 3 clique. It's covered. It's shown here in green, right? And then we kind of sort of start rolling with this clique, shifting it and making sure there is this intersection, that it remains, right? In this case, it should be 2 nodes, and we capture the next one. And we just keep doing it. We keep doing it until you cannot do it anymore, right? So it's a sort of this clique that starts rolling slowly, keeping, if it's 3 clique, it keeps 2 nodes common, right? And tries to replace 1 node with a new node, but such a way that what you get is also a clique. Now with triangles, it's actually quite easy because there are a lot of triangles in the graph. But with 4, for example, nodes, it's already not always happening. And so you kind of roll this until you get to the point where, like for example, like here, there is no way to move 1 node. If I move, say, this node, if I drop this node and pick up this node, this is already not a clique here, right? This is not an edge here. So that's sort of the concept for this algorithm, right? You try to find that clique and you start moving it until you sort of can, right? And that detects your community. Now, in algorithm itself, it's done slightly different. Instead of actually moving and doing this sort of rolling of the clique, you find those maximal cliques and you just look for overlap. And then you threshold this overlap at the value k-1. So if you have 4 cliques, you threshold at 3 nodes. And everything that less than 3 nodes, it just means you will not be able to roll through them. If you have 3 clique, you threshold at 2 nodes, and so on. And what you get as a result of the threshold, those connected components will be your communities. So this is what it looks like. We detect those cliques, the maximum cliques that are possible here. And what you see here, the number is the number of nodes, or the size of the clique. So, for example, the blue one, it's right here. This is, it's size 5 nodes. The red one is a 4 nodes clique. Where is it? Sorry, this is the red one, right? And so on, and say the brown one is 4 nodes clique. So you detect all those cliques, right? Maximal clique, and maximal clique is the largest possible clique for those nodes. And then you look for overlap for each of the clique, how many nodes they overlap with. For example, if I take say red clique, right? And I take the blue clique, they have in common this 3 nodes, and that's why there is this overlap 3. Or if I take, if I take a blue clique and green clique, they overlap with those 2 nodes, and that's what I put here. All right, and then we threshold them. And based on the algorithm, if it is k equal to 4, for example, I want to have a, the clique size 4, algorithm tell us threshold at value k-1, so threshold at 3. Come on. Threshold at 3, and then when it's above 3, I just leave 1, and when it's below 3, I would put 0, and then we get connected components, and there you go. So based on this 4 clique separation, this graph has to be, have 2 communities. One is this community, which is this one, and there is the rest of the graph. And so yes, it's overlapping community. Notice that there has been this node also belong, that sort of the split, right? It sort of doubled it here, so you can see it. So that's the k-clique percolation. Now it's actually quite interesting algorithm, and if we look at this 2 examples of the different graphs with a selection of this cliques, you notice that it works actually quite nicely, right? It splits the graph into this overlapping communities. Now, it's very clear that the performance and the result of this algorithm will strongly depend on the selection of the size of the clique, right? And so literally the authors recommend you to run it with, size 2, size 3, size 4, well, 2, you don't want to do it, but size 3, size 4, size 5, and see what happens. The denser the graph itself, probably the higher kind of clique number you can use to detect things. Now, the challenge, the problem with this algorithm that is insanely computationally complex, because you need to detect those cliques, and then you need to do everything else. And clique detection is computationally extremely expensive process. So this again will work on small graphs. But that's probably one of the very few algorithms that are designed for overlapping communities. Again, when you have large graphs, there is, most likely you don't have this overlapping communities. And so people typically use those graph partitioning approaches we talked before. But if for whatever reason you have overlapping communities, that's what you do. Now, If we go back to real-world networks, there's this interesting paper by Yuri Leskovec and Kevin Lang in 2010 when they analyzed the sort of the real-world social networks. I think this was from either Microsoft Messenger or Yahoo Graph, and they realized that. So what they did is they actually remember we looked at the metrics like normalized, cut, and one of the metric was conductance, and so they looked at the different partitioning of the nodes and measure the conductance of those cuts. And they found out that in real world graphs, typically optimal size, sort of the best size, the best partitioning happens, for nodes of size. And I think this number is like, probably a couple hundred. And so when you get larger cuts, larger communities, usually the quality drops. So when you have smaller communities, qualities also drop. So in a real world network, they're often like around 200 nodes. That's sort of the best communities that you detect. And the last slide today, I think it's actually, last slide. This actually from the review from 2000, probably 10 or 2015. And so if you notice all the ages, all the years of the algorithms, they're before 2010. Now there are many more algorithms that are out there. This is just a very, just a probably, I don't know, a third of algorithms that exist out there. But I think extremely important column here is this column, the right column, which is a computational complexity. And if you notice, most of the algorithms, they have this, for example, n cube, but there is m cube n, there is m4, there is n cube. Now this is all really bad because think about this, like any real graph is, well, at least 1,000 nodes. So you have to do computational complexity, tells you how many operations you need to do. So that like makes it 10 to the instantly, if it's 1,000 nodes, 10 to the third, 10 to the 9th computation. So it's already becomes almost non-computable. And if you take 1 million node graphs, that just doesn't work. But there are some algorithms like that, which is actually pretty good, right? And there is n log squared n, and this is the algorithm we actually considered, which really O of m. The reason is because we only measure, we only use modularity based on edges, and then it's because we do aggregation, it very quickly drops the complexity. But if you look at the, say, for example, at the algorithm for this for overlapping graphs, you get like exponential complexity. So that really works only for very small graphs. So bottom line. Community detection is defined as finding groups of nodes that are more tightly connected among themselves than with the rest of the graph. The definition is not precise, in the same way as with clustering, there can exist multiple solutions, and there is no single unique correct solution, and there are multiple algorithms that can produce it. Algorithms differ by the way they operate. Most of them are either greedy, heuristics, or some of them approximate. There's no exact solution. And algorithms differ widely in terms of their computational complexity. And so before you run something on a large graph, check the computational complexity of the algorithm, because you might wait forever for it to solve the problem. Now, typically in practice, yes, this is an algorithm by Blondel that you use as a sort of the first thing. It doesn't work well. Okay, you can try a bunch of other algorithms and just see which gives you better clusters according to your sort of understanding and your definition. And I think with that, we are done. Questions? So I would suggest you, if you're interested in this, look at the review, the community detection graphs. There is this review by Fortunata, and I think there is also a fresher review, probably I think from 2018, on more of of the algorithms. Okay, if there's no questions, we're done for today. Thank you. And there's going to be a seminar after the lecture. Thanks, guys.
Thank you.